I'm Takami Sato, a PhD student from UC Irvine, supervised by Professor Chi Alfred. Today, I will present our recent progress on our research on robustness of lane detection models to physical world adversarial attacks. In this work, we are targeting the automated lane centering system, ALC, which is a level 2 driving automation technology that can automatically steer a vehicle to keep it the center line. I think ALC is very common in nowadays, so I think some of them already experienced that because it's installed in the Tesla. To follow the traffic lane, so the camera-based lane detection is the essential technology of the ALC. So recently, several research demonstrate attack on the ALC. For example, the deload patch attack pretend to benign load patch, but the perturbation on the patch can fool the lane detection model like this, then it leads to out of the lane. I think it's hard to notice that for the driver's view. Another research demonstrates another attack, the placing sticker at the intersection, like without lane line. So because the intersection doesn't have lane line, so that if we put such a small sticker on the intersection, we can lead to the long lane. It should be very dangerous. Meanwhile, these attacks only target the particular ALC systems. For example, the deload patch attack on the open pilot, and the placing sticker attack. The placing should be there. Placing sticker attack demonstrated on the Tesla Model S. So we wonder whether all lane detection models are vulnerable to such attack. To study this, we are conducting this study, which is the first large-scale study to evaluate the robustness of the lane detection models on physical world adversarial attack in the driving scenario. So in the study, we cover 4 major types of the lane detection: the segmentation, low-wise classification, curve fitting, and anchor-based. And we evaluate 3 adversarial attacks on each lane detection method: the patch attack, white box patch attack, and the black box patch attack, and the black box drawing lane line attack. So in terms of the attack vector, we are evaluating 2 attack vectors: the patch attack, as shown in the before, so the patch is there, and it can disturb the lane detection a lot. And we also evaluate the drawing lane line attack. So we can see that which is a variant of the placing patch attack. It's less stealthy than the patch attack, but it's very intuitive, so the non-knowledgeable attacker can easily deploy it on the road. So throughout this study, we are seeking 3 questions. However, due to the time limit, we only explain the first 2. Is the black box attack is effective as the white box attack? It sounds very trivial, but the recent study showed that some black box attacks sometimes more effective than the white box attack. So we are also evaluating that. And the question is which attack vector is more effective to the attack. So this is the entire result. So I show the attack success rate for each attack on each lane detection models. So each row is for the attack, and each column is for each lane detection models. I will go through one by one. The first, for the white box attack, the white box attack is pretty effective on all lane detection models, which achieves 78%. This is very high. And secondly, the black box patch attack is less effective than the white box attack generally. But interestingly, the anchor-based method is, sorry, maybe the voice is not that clear. So the black box attack is the anchor-based method to keep the high attack success rate even in the black box attack. Now finally, we evaluate the black box drawing lane line attack. Interestingly, the segmentation and the curve fitting method show the higher robustness. And interestingly, we found that these are actually installed in the real product. For example, the segmentation model is used in the Tesla, and the curve fitting method used in the open pilot. So I think the manufacturer fortunately avoids such kind of the less robust models. It's good for us, and I'm happy to know that. So I covered the first two questions in the previous slide. For RQs, for the final research questions, so I briefly explained. So the transfer-based attacks are generally keeps the high attack success rate. And interestingly, sometimes the transfer-based, the drawing lane line attacks is much more effective than the normal drawing lane line, black box drawing lane line attack, which means that some models are somehow robust, so it's hard to find the effective attack during the optimization. But the other models are more vulnerable to such attack, then we can find such vulnerability throughout the other less robust model. It was really interesting for us. So conclusion, we conducted the measurement study on lane detection models for the future work, so that we plan to evaluate more dataset and more model, and design more effective black box attack. And we also evaluate more the defense mechanism on it to solve this problem. Thank you for listening. Now I am open to questions.